For our case study, we will be analyzing some of the potential processes involved in manufacturing components of the Chicago Rotary rock tumbler. Shown here is the body of the tumbler, which is made up of several pieces of sheet metal. The bottom corners have been bent by a sheet metal roll forming process, as indicated by a large radius bend. The top corners have been bent with a sheet metal brake, judging by the straight 90-degree bends with small radius. After bending, the sheets were joined by resistance spot welding, as indicated by the small circular weld marks shown here. Here we see examples of sheet metal punching operations using custom dies. The holes could have alternatively been drilled or milled, however the rectangular hole geometry is not obtainable through these processes, which indicates it is most likely to have been punched. Also, drilling tends to leave behind more burrs, and also typically has a slower production rate. Additionally, the indicated thread holes were tapped after the punching operation. The parts shown here are likely blanked out of sheet metal, as indicated by the uniform wall thickness, as well as the slight burrs and imperfections on the edges. To achieve the concave geometry, these parts were then deep drawn. As an alternative process, these parts could have been casted. This is unlikely because a parting line or casting flash is not present. Also, a casting process would be less desirable because the production rate is lower and the process is generally more costly in large quantities. Finally, the holes were punched either prior or post deep drawing, or at the same time using a compound die. Here we see a shaft that was likely machined from extruded bar stock. After turning down the diameter on a lathe, the flat keyway feature was milled as indicated by the feed marks. Alternatively, this piece could have been die casted. However, since casting inherently leaves a parting line, this would not be desirable or usable as cast, and would still require a post-process turning and facing operation to clean up and ensure proper geometry as well as finish. It is more efficient and economical to perform all these operations consecutively on a lathe. Finally, the part was electroplated with what looks to be zinc plating. Here is an example of some plastic molded parts. The round ejector pin marks shown here indicate an injection molding operation. Here is another example of injection molded plastic parts. This part is composed of two separate injection molded parts that have been joined by an ultrasonic welding process, as indicated by the melted plastic at the flat surface junction where they are joined. The discontinuous parting lines also indicate that this was two separate parts. This part could have alternatively been 3D printed, however this process is expensive and has a slow rate of production, which makes injection molding more cost effective. The presence of ejector pin marks and parting lines are also evidence that this part was injection molded and not 3D printed. This concludes our case study.